Welcome to today's Explainer, everyone. I'm absolutely thrilled to have you here, because we're jumping right into something I find endlessly fascinating: the anatomy-to-action journey of robotic movement. If you've ever spent time observing modern automated machinery, you know we're living in an era entirely defined by high-throughput manufacturing, aerospace precision, and autonomous systems operating at, honestly, unimaginable scales. Well, today we're moving way beyond the basics. We're going to break down exactly how these sophisticated systems come together to move with such deliberate, purposeful accuracy. We're going to completely deconstruct the integration of sensors, actuators, and controllers that literally make modern automation possible. Let's get into it.
So I want you to start by thinking about this seemingly simple question. How does a robot actually know exactly where its arm is? I mean, think about the sheer complexity of this for a second. Picture a robotic arm on an assembly line, seamlessly welding a car chassis, or maybe a medical robot assisting in a super delicate, minimally invasive surgery. The level of precision required there is just staggering. How does a machine, which is really just a bunch of machined metal, rare earth magnets, and copper wiring, know precisely where its appendage is in three-dimensional space at any given millisecond? Achieving that kind of sub-millimeter precision requires this incredible symphony of hardware and software working in perfect tandem. And to truly understand the action and the intelligence of these machines, we first need to look at the physical body of the robot itself.
Section 1. Anatomy of a robotic arm. To understand the action, we first need to look at the physical body of the robot.
Okay, let's dive into this. Every dynamic movement in a robotic system relies on a rock-solid, highly engineered foundation. Starting down at the bottom, we have the arm base. Now, this isn't just a static mount, right? The base provides the absolutely critical structural integrity needed to withstand the massive shifting torque generated by the whole system above it when it's whipping heavy payloads around. Extending up from that base, we have the linear actuator. This is the component that allows for precise Cartesian extension, basically giving the arm its necessary reach across a physical workspace. Moving along the structure, we hit the DC motor. This is the raw kinematic powerhouse of the whole setup. It's what drives the rotational motion of the arm segments. And finally, way at the end of the kinematic chain, we have the robot gripper, or what's often called the end effector. This is the specific tool that actually interacts with the environment and manipulates objects.
Now, what connects all these structural segments and actually enables the articulation? The joints. Specifically, the revolute joint. A revolute joint operates by allowing rotation about a single, highly constrained axis. Its entire mechanical purpose in life is to control angular position accurately. When you combine multiple revolute joints across an arm, you start building out degrees of freedom, which is really the fundamental building block of complex 3D movement in space. But here's the catch. A joint, on its own, is essentially dead weight. It's just a hinge. Achieving accurate single-axis rotation requires that the joint be paired seamlessly with both active actuation and real-time telemetry. To understand how that teamwork actually functions, it kind of helps to think of the robot in almost biological terms.
Moving to Section 2, Senses, Muscles, and Brains. Let's see how these physical parts act as biological equivalents.
And this brilliantly illustrates the exact contrast we're talking about here. The system relies on two critical hardware counterparts to bring that revolute joint to life. First, we have the senses, represented by position sensors, which are most commonly high-resolution rotary encoders. As the joint physically rotates, these encoders measure the angular position by generating thousands of electrical pulses per revolution. The system uses these pulses to parse micro-movements into digital data. It's quite literally feeling its way through space. Countering that, we have the robot's muscles, the DC motor. The motor's whole job is to drive the joint to a desired angular position by transforming electrical energy directly into mechanical torque. So you have the sensor continuously mapping physical movement into data, while the motor continuously forces physical movement based on electrical power.
But as you can probably guess, these highly tuned senses and powerful muscles don't mean much without a central processing core to coordinate them. Enter the control system, the ultimate brain of our automated setup. The control system continuously ingests the telemetry data streaming in from the position sensor, which establishes exactly where the arm currently is, and it cross-references that against the desired angular position, which is where it actually needs to be. And this isn't just a one-and-done calculation. The control system acts as a relentless, continuous comparison engine. It's running at incredibly high frequencies, constantly checking reality against its target, and generating highly specific control signals to dynamically adjust the motor's speed and direction. So how does this brain actually operate in the midst of real-world physical forces? Well, let's walk through a concrete technical scenario.
Section 3. The 6-step control loop. Let's see this continuous comparison in action.
All right, let's establish a specific operational parameter for our scenario. We need our robotic arm to move to a precise target angle of exactly 45 degrees. Step 1 of our control loop kicks off when the system polls the environment to establish its current state. The position sensor executes a rapid read of the joint's actual physical position and shoots a pulse train back to the controller. Let's say, for this scenario, the sensor telemetry tells us the arm is currently resting at exactly 30 degrees. So right off the bat, we've got a quantified gap between our present reality, 30 degrees, and our programmed target of 45.
So the crucial point here is this 15-degree gap. In step 2, the controller instantly processes those two data points to establish the error delta. By simply subtracting the current 30-degree position from the desired 45-degree target, the system identifies a 15-degree delta. This error margin is the exact mathematical representation of the physical work that still needs to be done. The system now has a highly precise quantified metric of exactly how far out of alignment the joint currently is.
Now, to bridge that 15-degree gap, the controller has to translate that mathematical error into physical action. That's step 3. Based on the size and direction of the delta, the controller generates a very specific control signal. Because the joint needs to increase its angle to hit the target, the controller dispatches a positive voltage signal down to the motor. The polarity of this voltage tells the motor which direction to rotate, and the amplitude, or the strength of the voltage, often scales with the size of the air, meaning the motor is going to push a lot harder when the area is large, and it'll ease up gently as it gets closer to the final goal.
Which brings us to the actual mechanical execution in steps 4 and 5. In step 4, the motor receives that positive voltage, it fires up, and it applies mechanical torque to physically rotate the joint. But here's the critical part. In step 5, the position sensor is simultaneously running a continuous real-time update loop. Fraction of a millisecond by fraction of a millisecond, that encoder is screaming data back to the brain as the arm sweeps from 30 to 32 to 35 degrees. This shows you the incredible real-time agility of the system. It's constantly observing the immediate physical results of its own motor outputs.
Let's zoom out and see how this all builds together. We see these individual steps form a relentless, interconnected cycle. Steps 1 through 5 build the foundation, sure, but step 6 is the real linchpin here. Repeat steps 2 through 5. Now, why must this be a closed feedback loop? Why not just send a single linear command to move 15 degrees and be done with it? Because, well, the real world is messy. A robotic arm has to deal with variable payload weights, friction, kinetic inertia. If it operated on an open loop, the momentum of a heavy load could easily cause the arm to blow right past 45 degrees, resulting in a massive catastrophic overshoot. By continuously calculating that shrinking error delta and dynamically adjusting the control signal hundreds of times a second, this closed loop guarantees absolute controlled precision. Ultimately, all of this relentless, cyclical adjustment leads to exactly what we want: zero error. As the arm's physical position perfectly matches that 45-degree target, the calculated error drops to absolute zero. The controller, seeing no remaining delta, instantly neutralizes the control signal, which halts the motor right on the dot. And the real-world implications of this zero-error resolution are profound. This exact mathematical stability is what allows a surgical robot to stop a scalpel mere millimeters before it touches a vital nerve. It's what enables an aerospace welding arm to perfectly join heavy fuselage panels without compromising any structural integrity. It's pretty amazing.
It really is an elegantly brutal piece of engineering when you break it down into these interdependent parts, isn't it? But I want to leave you with a broader concept to chew on today. If an automated system continuously monitors its own state, mathematically compares it to an ideal goal, and dynamically corrects its own output until the variance reaches zero, what else could this closed-loop logic optimize? Because once you grasp the sheer power of calculating deltas and applying continuous real-time correction, you realize this isn't just about robotics anymore. This is the exact same underlying logic governing autonomous driving algorithms, industrial climate control systems, and even complex economic models. The entire modern world is built on closing the loop.